to commence from where we left off the last time. Okay, so what we're going to talk about here are molecular orbitals. And that's in relation to the type of bonding that we talked about earlier. If you remember, we talked about the sigma bonds and the pi bonds, and this is directly related to that. Now, if you remember, was it chapter 7? We talked about atomic orbitals. Well, we have the corresponding molecular orbitals, and orbitals are basically, as we said before, a region in space where we find that the probability of finding an electron is very high. So that is true for both atomic and molecular orbitals. Now, when it comes to molecular orbitals, there are essentially two types based on the combination of atomic orbitals. You have what is known as the bonding orbitals, and then you have what is known as the anti-bonding orbitals, all right? And in terms of how we assign electrons to molecular orbitals, we follow the Aufbau principle just as we did when it comes to determining how the electrons are distributed among atomic orbitals. So those same principles will apply when it comes to molecular orbitals. So what we're going to do is look at the simplest examples of molecular orbitals. We're looking at the orbitals formed when you have hydrogen, the hydrogen molecule being formed from two hydrogen atoms. So what you see here on the screen to the left are the two 1s orbitals of two different hydrogen atoms that will overlap to form a bond. And you'll notice that in order for the overlap to take place, the electrons must be spinning in opposite directions to begin with. So when these overlap, right, when these two orbitals overlap, you end up with two orbitals being created, two molecular orbitals being created. One is the bonding molecular orbital, which is down here, and the other one is the anti-bonding molecular orbital, all right? So these two electrons that were originally between the two atomic orbitals coming together, those two electrons in a ground state will simply go into the lower energy or the most stable molecular orbital, which would be the bonding molecular orbital. Now, in terms of the difference between the two, what you'll find is that the bonding molecular orbital in each case will be more stable than the anti-bonding molecular orbital. And the reason why is because in the case of the bonding molecular orbital, what you'll have is an enhanced region of electron density between the two nuclei, all right? So that is what is seen here, okay, in the case of a bonding molecular orbital. In the case of the anti-bonding molecular orbital, what you'll have is the opposite, a region of diminished electron density between the two nuclei, all right? And that is more unstable and therefore of a higher energy, all right? So basically when you have the two electrons coming into the bonding molecular orbital, the resulting structure will be stable. Now, each time an electron goes into an anti-bonding molecular orbital, then the resulting structure would be each time be more and more unstable. Excuse me. Okay, so that's basically some initial introduction into the concept of molecular orbitals bonding and non-bonding, or anti-bonding, I should say, all right? So when it comes to the overlap of p orbitals, then these are the possibilities that you'll see. And we talked about this earlier, but we're going to go into it in more detail. So in the case of an end-to-end overlap between two p orbitals, such as these two px orbitals here, then you're going to end up with, of course, a bonding and anti-bonding molecular orbital. So this is called the sigma 2p bonding molecular orbital because they're formed from 2p orbitals. And this would be the sigma star anti-bonding. Now this star here, I think I should have mentioned it before. Let me go back here. Yes, there's a star here, which is indicating that it's anti-bonding, all right? So whenever you see the sigma star there, you should immediately understand that we're talking about an anti-bonding molecular orbital. So when these 2p orbitals overlap end to end, you're going to end up with your sigma 2p bonding and your sigma 2p anti-bonding. Now, if they overlap parallel side by side, as you can see here between these two 2pz orbitals, then you're going to end up with your pi bonding 2p orbital and your pi 2p anti-bonding orbital, all right? And the same thing will be true for these two py orbitals that will be overlapping sideways like that. Again, you're going to end up with your pi 2p bonding and pi 2p anti-bonding. All right, so those are the possibilities when it comes to the p orbitals. And there are other possibilities for the higher orbitals, the d, f, and so on. But at this level, we won't get into those. All right. So going back to the hydrogen example, but in this case, we're talking about the hydrogen H2 plus ion. So there's only one electron. So we have a hydrogen 1s orbital here, another one here. When they overlap, you're going to have your sigma 1s and sigma 1s star anti-bonding. And the one electron that was here will now just simply end up in the sigma 1s orbital. All right. And it turns out that this is not as stable. I'm sorry. This is not as stable as in the case of the H2 molecule. In fact, there is a formula, very simple formula. Where's the pen? That you can use to calculate the bond order in these situations. So the bond order, based on a diagram such as this, would be equal to half times the number of bonding electrons minus the number of anti-bonding electrons. Oh, I guess I forgot to share my screen. So let me do that now. I'm sorry about that. Okay, can you see my screen?
Yes.
Okay. I keep forgetting. All right, so going back to this here. In fact, let me go back to this here. I talked about the hydrogen molecule, bonding, anti-bonding molecular orbitals. All right. And then I spoke about these possibilities for the 2p orbitals, right? In the case of the 2px here, it will form the sigma bonding and anti-bonding orbitals. And in the case of the 2pz's and the 2py's, bonding and anti-bonding pi orbitals. Okay, so I was saying here that to calculate the bond order, remember the bond order is basically the multiplicity of the bonds, double, triple, single. That can be calculated based on this diagram. It is equal to half the number of bonding electrons minus the number of anti-bonding, electrons. All right. So for example, in the case of the in the case of the hydrogen molecule, the bond order will be equal to half of 2, because there are 2 electrons in the bonding orbital, minus 0. So that will be equal to 1. So what that tells you is that there's a single bond in the case of the hydrogen molecule. All right. Now, in the case of the H2 plus ion shown here, the bond order would be equal to half the number of bonding electrons, which is 1, minus 0. So that would be equal to half. So in other words, this would be, and I'm going to put this in quotations, half a bond. All right. So therefore, this explains why this species here is unstable and the hydrogen molecule is stable, because the bond here is basically weaker. It's a half a bond in the case of the H2 plus ion, whereas in the case of the hydrogen molecule, it's a single bond, and therefore that structure will be a more stable structure. So that's why the hydrogen molecule is stable while the H2 plus is not. All right. This is just mentioning that in all cases, the anti-bonding molecular orbitals are of a higher energy compared to the bonding molecular orbitals. All right. So therefore, whenever an electron goes into the bonding molecular orbitals, it adds stability to the structure. But whenever an electron goes into the anti-bonding molecular orbital, it makes the structure that much that less stable. All right. So what you're going to see here now on this screen is a series of diatomic molecules from the second period and their corresponding electron distribution in terms of the molecular orbitals. All right. So in the case of the lithium molecule, Li2 molecule, You have 2 electrons going into the sigma 2s orbital. Well, before I even go into that, let me just show you or just point out to you the order of energies of the different orbitals. So the lowest orbital here will be sigma 2s. Then you have sigma anti-bonding 2s. Then you have pi 2p's, there are 2 of them, which are both bonding. Then you have the sigma bonding. Then you have the pi 2p's, 2 of them anti-bonding. And here you have the sigma anti-bonding. Now, the order of the orbitals are identical from lithium to carbon. But when you get to, from lithium to nitrogen. But when you get to oxygen, what you'll notice is that in the case of these 2 sets of orbitals, they're flipped, all right? And there's a reason for that, which I won't go into right now, but basically the sigma 2p orbital that is present in the nitrogen will be of a lower energy in the case of oxygen, and the pi 2p orbitals will be of a higher energy. So that's why you have that flipping from here. Oops. This goes here, this goes here to get the order that you observe in the case of oxygen, all right? And then the order that is seen in oxygen in terms of the energies of the molecular orbitals continue to fluorine and to neon, all right? So whenever it comes to assigning electrons, you do so according to the Aufbau principle. So let me show you how that is done. Give me a minute here. Let me just do a little juggling with my other computer here so I can do this properly. Come on. Okay. Oh, shoot. Okay. So, okay, so chapter 10. Okay, what's going on here? Okay, so let me get out of this here and go to my writing pad here. Let me remove this. So in the case of, I'm going to just choose one arbitrary diatomic molecule from period 2. So let's say we want to look at nitrogen. So in the case of nitrogen, you're going to have your sigma 1s here, and then your sigma 2s, not 1s. This should be 2s. This should be 2s. Anti-bonding, so I'll put a star here. And then in the case of the next set of orbital, that would be the pi 2p bonding, and then sigma 2p bonding, and then the next would be the pi 2p anti-bonding, and then the next one would be the sigma 2p anti-bonding, all right? So these are the orbitals and how they're distributed in the case of the nitrogen molecule. Now the atomic number of nitrogen is 7, and there are 2 of them. So therefore for N2, the total number of electrons would be 14. And the first 2 would go into the 1s orbital, which would be, which would not be, actually what I should be looking for is the valence electron, because all these orbitals here are in the valence shells. So the total number of electrons here would be 10 because nitrogen is in group 5. So we have 10 electrons to assign. So the way we assign the 10 electrons would be 1, 2, then 3, 4, then 5, 6, 7, 8, 9, 10. All right? So that's basically how the electrons are assigned in the valence shell among the molecular orbitals in the case of the nitrogen molecule. Now, to calculate the bonding order in this structure, that would be half the number of bonding electrons. So let's look at the total number of bonding electrons. We have 2, 4, 6, and 8. Oh, actually, no, 2, 4, 6, all right? Oh, and 8 up here, I'm sorry. We have 8 bonding electrons here. So half of 8 minus the number of anti-bonding electrons, which would be only these 2 right here. So let me put that in a square to make a distinction. So that would be 2 here. So therefore, this works out to be equal to 3. And that's why, based on this theory, we know that there's a triple bond in the case of the nitrogen molecule, the N2 molecule, all right? So that's what happens in the case of the nitrogen molecule. Now, if we do the same exercise in the case of the oxygen molecule, right? The group number of oxygen is 6, but it's O2, so there's a total of 12 electrons. So therefore, it's the same as this, but we have to add 2 more electrons, and those 2 electrons will go here and here in the pi2, 2p anti-bonding orbital. So therefore, if we were to calculate the bond order for this structure, that would be equal to the total number of bonding electrons, which would be 2, 4, 6, 8, as we said before, minus the total number of anti-bonding electrons, which would be 2 plus 2, which would be 4, which means that the bond order for this structure will be half of 8 minus 4. 8 minus 4 is 4, half of that is 2. So therefore, this would be 2. And therefore, the type of bond that exists in the oxygen molecule is the double bond. So in the case of oxygen, it's a double bond, a double bond that will exist between the 2 oxygen atoms, all right? So that explains why oxygen has a double bond between the 2 atoms in its structure. Okay, let me do another example now. And this example is boron. So in order for me to do this, I have to erase, you know what, let me just clean up everything here. Okay, so in the case of boron, boron has 3 electrons on its outer shell. So therefore, for the boron molecule, that would be 6. So in the case of how the orbitals are arranged in the boron molecule, you're going to have the sigma 2s here, and then you're going to have the sigma 2s anti-bonding, and then you're going to have your pi 2p orbitals, which are bonding, and then you're going to have your sigma 2p, which is also bonding, and then up here you're going to have your pi 2p's, which are anti-bonding, and then up here you're going to have your sigma 2p anti-bonding, all right? So that's the order of the orbitals in the case of boron. So if you start assigning the electrons, the first 2 would go here, the next 2 would go here, and then the next 2 would go here, all right, and here. So in this case, the bond order would be equal to half the number of bonding electrons, which would be 2 plus 2, so that's 4, minus 2 for the anti-bonding molecular orbital here. So this gives you a grand total of half of 2 will be 1. So therefore, the bond order is 1, which means that there will be a single bond in the case of the boron diatomic molecule. All right. So that's what happens in that case. Now, let me take the one just before boron in the case of helium. I'm sorry, beryllium. So let me erase this here. erase this here, here. So in the case of beryllium, total number of electrons would be 2 in the valence shell. So that means for the beryllium molecule, that would be 4. So what happens in the case of beryllium? You won't have these 2 electrons here. All right, these 2 electrons will not be here. So what does that mean? That means that the bond order will be half the number of bonding electrons, which is 2, and minus the number of non-bonding electrons, number of anti-bonding electrons, which is 2. So therefore, in this case, in the case of beryllium, the bond order is 0. And what that tells you is that there's no bond between the 2 atoms in this supposed molecule. And in fact, nobody has been able to, as far as I know, I haven't checked recently, but as far as I know, nobody has been able to create, under any conditions, the beryllium-2 molecule. And the reason for that is that basically, based on the molecular orbital theory, the bond order would be seen to be 0. All right, so basically no stable structure or no structure at all have been created which looks like the beryllium diatomic molecule. Okay, so that's basically how we determine the electron distribution for molecules, all right? Diatomic molecules from, let me see here. Oh, wrong slide. Right, so nobody has been able to determine or create the Be2 structure. And basically what we just discussed is why is it that that is so based on the molecular orbital theory, all right? So I would say the key thing for you to remember about this is that you need to remember the order of the orbitals as you go from lithium to neon, and also the corresponding valence shells orbitals for the other elements, corresponding elements below. Key thing you need to remember also is that when you go from nitrogen to oxygen, there's a switch between the sigma 2p and the pi 2p orbitals in terms of their energy, all right? So in the case of nitrogen, the sigma 2p is above the pi 2p's, but in the case of oxygen, it is flipped. The pi 2p's now end up being of a greater energy compared to the sigma 2p's. Okay, now one more thing I want to say before I leave this slide. Remember we talked about the paramagnetism phenomena, all right? Let me make this full screen. So remember we said that, let me squeeze it here. If you have a structure that is paramagnetic, right? That basically indicates that the structure has unpaired electrons. Any structure with unpaired electrons in the electron configuration among the orbitals would be paramagnetic. Now, the reason I mentioned that is because I showed you a video some time ago, and I'm going to show you again just to remind you of an experiment that is used to determine whether or not a substance is paramagnetic. And if you remember in that video, the 2 experimenters were using nitrogen and oxygen, liquid nitrogen and liquid oxygen as examples, all right? Now, before I show you the video again, I want to point out a particular feature of the orbital distribution, the electron distribution among the orbitals for nitrogen and oxygen molecules. You'll notice here that in the case of the oxygen molecule, you have 2 unpaired electrons right here, all right? These electrons are occupying molecular orbitals singly by themselves, and therefore they're unpaired, all right? There's no such arrangement in the case of the nitrogen molecule. There are no unpaired electrons in the case of the nitrogen molecule structure. So therefore, we can make the prediction that the oxygen molecule will be paramagnetic and the nitrogen molecule will not be paramagnetic, not paramagnetic, all right? So that is confirmed by the experiment that I showed you in the video, and I'm going to show you again. I'm going to copy this URL. And I'm going to place it here. And okay, let me stop here for a minute. And let me plug in the speaker and bump up the volume.
This is a test tube of liquid nitrogen.
And this is the test tube of liquid oxygen.
Let's see what happens when we pour the liquids past the poles of a strong magnet.
Okay.
Now, liquid nitrogen isn't normally magnetic, but each of the nitrogen molecules acts like a tiny magnet when it's exposed to a magnetic field. This effect is known as diamagnetism. That's just a fancy way of saying that each of the nitrogen molecules is repelled by the magnet's magnetic field. So when I pour the liquid nitrogen past the magnet's poles, it doesn't look like anything special happens. The nitrogen just falls past the magnet. That's because the diamagnetic effect is very weak, so we don't normally observe it. All materials are at least slightly diamagnetic, but because the effect is so tiny, we don't normally notice it.
Just like nitrogen, oxygen isn't normally magnetic. And just like nitrogen, each molecule of oxygen behaves like a tiny magnet when it's exposed to a magnet's magnetic field. Oxygen behaves differently than nitrogen, though. The way oxygen behaves is called paramagnetism. That's a fancy way of saying that each molecule of oxygen is attracted to a magnet's magnetic field. So when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
Thanks for watching. I hope you'll join us again soon for another experiment.
Let's try that with liquid nitrogen at the same time.
Okay.
Hey.
Oh.
Okay, I'm going to stop. Hold on 1 minute. Okay, so that's basically demonstrating experimentally, yet again, the fact that oxygen is paramagnetic and nitrogen is not. And as I said before, the reason why that is so, going back to this here, is that oxygen has unpaired electrons in its electronic structure, while nitrogen does not have unpaired electrons. So therefore, that's the reason why oxygen is paramagnetic and nitrogen is not. So basically, if you want to predict whether or not a structure or a molecule is paramagnetic, you basically have to draw the electron configuration for the molecular orbitals, all right? So that's basically what you need to do. And then once you assign the electrons, you determine whether or not there are any unpaired electrons, and therefore, if there's such unpaired electrons, then you can conclude that the structure is paramagnetic. Okay, what next? Okay, so I think this will be the last topic in this chapter, and this is talking about the bonding in benzene, all right? And for those of you who plan to do organic chemistry, you'll be meeting this again, I think in organic 2, if not organic 1. I'm quite sure it's organic 2, but it depends on who is teaching it basically. So basically, benzene was a bit of a mystery of a compound when it was first discovered, right? When Michael Faraday discovered it, everybody determined that the molecular formula for benzene is C6H6. And then there was a big rush on to find out, okay, what exactly is the structure, how the atoms are connected to each other. And people came up with different ideas. And it was not until Kekulé, who claimed that the idea came to him in a dream in 1865, he came up with the structure of benzene, which we're now familiar with today. So this is the structure of benzene. And as you can see, it is a 6-membered ring. And according to the structure that Kekulé came up with, you have an alternating double, single, double bond around the structure. All right. So this was the first original structure, which basically satisfied not only the formula that was discovered first, but also certain chemical properties. However, we now know that this is not the true structure, right? This is one of two possible structures, and the hybrid structure is the real structure. So the ideas behind the concept of resonance comes into play when it comes to explaining the benzene structure. So here we have the 6-membered ring, which is one representation of benzene. And then if we shift the electrons between the bonds like this in this structure, then you end up with the other structure, right? So the real structure is a hybrid, all right, between these two, all right? So what that means is that the hybrid has some common characteristics with one structure and other characteristics it shares with the other structure, all right? And the term that we use to describe the real structure in terms of how the electrons are arranged, we say that the electrons are delocalized, a very important concept that will become important, as I said before, when you get into organic chemistry. So the resonance hybrid structure of benzene is oftentimes represented by this, all right? So this represents the true structure of benzene. But what you'll find in organic chemistry is that we still use these two structures because they're useful for explaining and predicting certain reactions that benzene and other benzene type compounds will undergo, all right? Okay, so in terms of the actual Lewis structure of benzene, we now know that each carbon atom in the benzene molecule is sp2 hybridized, right? Which means that you have 3 sp2 hybrid orbitals for each carbon atom. Now, for each carbon atom, one of these sp2 orbitals will overlap with a 1s orbital of a hydrogen atom, all right? So we have that overlap here, 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 and here. And these orbitals, because of the nature of their overlap, they're all sigma orbitals. Sigma, 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 and sigma, all right? So we call this a sigma framework because not only do we have sigma bonds formed between the carbon and the hydrogens, but we have the sigma bonds formed between the carbon atoms by the overlap of sp2 hybrid orbitals from each carbon. So this is a sigma bond right here between these two carbons. You have a sigma bond here, a sigma bond here, a sigma bond here, a sigma bond here. All right? No, not here, I'm sorry, here. All right? So we have sigma bonds between the carbon and each hydrogens, and we have sigma bonds between the carbon atoms themselves, all right? Okay, so that's what we call the sigma framework. So this brings the question, well, what about the unaffected p orbital, which exists on each carbon? So you have a p orbital here, above and below, a p orbital here, a p orbital here, a p orbital here, p orbital here, and finally, a p orbital here. All right? So what will happen is that you're going to have overlap sideways. Whoops, sorry. Press down too hard on the pen. Overlap here, overlap here, overlap here, and overlap here. And finally, well, not finally, overlap here, and overlap here. And as a result of the sideways overlap of the p orbitals here, we have what we call a pi system, a delocalized pi system. Let me add delocalized here. And the reason why we use this term delocalized is because the electrons within this pi system do not belong to any particular carbon atom. Basically, it forms a ring above and below the sigma framework established already by the sigma bonds between the carbon atoms. Okay, now this looks a bit confusing, I must admit, all right? But you know what? Let me see if I can find a better picture. Let me go here. delocalized pi system, benzene. Okay, so let me see if I can find some images here. Okay, here's a good image right here. Let me click on this. Oh, better yet, here's a better image. This is much better. So let me click on that, see if I can get that to look larger. Okay, what's going on here? Okay, let me see here. Okay, let me not waste any time on that. Sorry about that. I thought that would be a good picture to show you guys. Let me see if I can make this larger. Okay, this is not as good as the one I thought I would be able to show you, but so basically, as I said before, after you've established the sigma framework, which looks like this, these are the p orbitals which are unaffected by hybridization, and they will overlap sideways right across or right around the ring for both the top and the bottom of the ring, and you're going to end up with your pi system, your delocalized pi system, which is represented by what you see here in the case of structure C, all right? And that is basically the true structure, what we now accept in chemistry, organic chemistry especially, as the true structure of the benzene molecule, all right? However, as I said before, we usually use the Kekulé structures when it comes to explaining certain reactions when it comes to benzene and derivatives of benzene, all right? So these are just some examples of compounds that we call aromatic compounds. Aromatic compounds in chemistry basically refers to compounds such as benzene that has a ring structure with a delocalized system of pi electrons, right? That's basically what we mean by an aromatic compounds. The actual definition is a bit more complex than that, but that's generally what the definition is, all right? So benzene is considered to be aromatic, and all these other compounds like aniline, benzoic acid, and so on are all considered to be aromatic. You might be wondering where this term aromatic comes from. And it comes from the fact that before, back in the day, most of the compounds with these systems tend to have pleasant odors, and therefore they're called aromatic. But of course, there are other compounds which are not as pleasant smelling, which do have that same system. So basically in organic chemistry, the term aromatic is referring to systems which have a ring of delocalized pi electrons in the system, all right? Okay, and that's basically it for this chapter 10, all right? So any questions before we move on to chapter 11? Okay, so let's see, what time is it? 10:08, okay. So in the case of chapter 11, which by the way is the very last chapter for this course, we'll be talking about, hold on, oops. States of matter, and in particular, we'll be talking about solid and liquid states because we already covered the gaseous state in chapter 5, I think, all right? So here we'll be talking about the type of intermolecular forces that exist between molecules and ions, and the states of matter, solids, liquids, and gases, but we'll be focused on solids and liquids because we talked about gases before. So when we talk about intermolecular forces, as the term suggests, that means forces between molecules. And it's very important that you're able to distinguish between intermolecular forces and intramolecular forces, all right? So intramolecular forces are forces that exist within a particular molecular structure, right? And these are basically covalent bonds for the most part, all right? And of course, these bonds and their directions will impart certain properties to the substance that it represents. So those are intramolecular forces. The intermolecular forces are those forces that exist between molecules, all right? And what you'll find is that there's a correlation between these forces and the type of physical properties that solids and liquids especially display, all right? So for example, in the case of the water molecule, which is a simple molecule, one oxygen connected to two hydrogen atoms, the intermolecular forces would be the forces between the oxygen and the hydrogen atoms, which would be the covalent bonds, right? On the other hand, you have forces that exist between individual water molecules. And more specifically, what you'll find, for example, is that there will be a force of attraction between the oxygen of one water molecule and the hydrogen of another water molecule. So that force that exists between the atoms from different molecules are known as intermolecular forces, all right? And another force of that type is shown here, right? Between the oxygen and hydrogen, between the oxygen and hydrogen, and so on and so forth, right? So those are intermolecular forces. And what we're going to see in this chapter is that there are different intermolecular forces that exist in between covalent molecules. Okay, so let's talk about some general properties of the different states of matter. And we all know this before from your previous high school chemistry or introductory chemistry. When it comes to gases, they tend to fill the container that they're in. And in terms of the microscopic particles, their movements or motion would be basically rapid and random motion, moving at high speeds, occasionally bumping into each other and bumping into the walls of the container, right? So the type of motion that these particles will undergo is mainly translational. In other words, straight line motion unless they hit each other or hit the walls of the container, all right? So that's how gases behave. Now, in the case of liquids, they tend to be, less energetic, right? They move more slowly, and they basically rub against each other as they move, or they slide against each other as they move. Their motion is mainly translational, but of course, again, it can be affected. Their trajectory can be affected by the occasional bumping into each other. So therefore, because of these particular characteristics of the liquid state, they tend to have a fixed volume, and they tend to flow and assume the shape of the container that they're in, right? So that's basically what happens in the liquid state. And then in the solid state, it's a more rigid arrangement where the particles occupy fixed positions relative to each other. And the forces hold the particles in such a shape. So these particles are even less energetic compared to the liquid state, all right? And as a result, the properties imparted to substances in the solid state, they will be of a fixed volume, a definite shape, and they're less compressible than liquids, all right? So that's just a summary of the different types of intermolecular forces that exist between the particles in the gaseous, liquid, and solid state, all right? As I said before, we'll be focused in this chapter on the liquid and solid state because we talked about gases. We went through a whole discussion about gas laws and all that good stuff. So we won't be talking that much about gases. We'll refer to it from time to time, but the focus of this chapter would be the solid and the liquid state. Okay, so let's talk about certain terms. Again, these are terms you should have met before in reference to the change in state. So if we're talking about a liquid, let's say water, and it basically goes into the gaseous state, then that process is called vaporization. And that process requires enthalpy or energy, and therefore we can quantify the amount of enthalpy that is needed for that change, and that is called the enthalpy of vaporization, which by definition is the amount of heat that must be absorbed to vaporize a given amount of liquid at a constant temperature. So to go from H2O liquid to H2O gas, the enthalpy of vaporization for that process is given right here. It's 44 kilojoules per mole. And please note that there's a plus sign here, which indicates that this transformation is an endothermic transformation. In other words, heat is required in order to convert the liquid to the gaseous state. So that's what enthalpy of vaporization is. And then condensation is basically the reverse, right? Going from the gaseous state to liquid state, which is shown here. And of course, if going from liquid to gaseous is endothermic, that means that going from gaseous to liquid is exothermic, but the magnitude of that quantity is the same, 44 kilojoules per mole, all right? So that's basically what we mean by the terms vaporization and condensation. All right. Okay. Now, because enthalpy is a state function, what that means is that going from vaporization and then reversing the process by condensation, the total enthalpy change of that process must be equal to 0. If you go from the liquid to the gas and then back from the gas to the liquid, then basically the total enthalpy change for that process would be 0. And these are just some other substances in this short table with their corresponding enthalpy of vaporization values. All right, so for each of these are the values, the energy values needed to convert 1 mole of each of these substances from a gaseous state to the liquid state. All right, and okay, so that's that. Let's talk about this concept of vapor pressure. Vapor pressure is the pressure of a liquid, or I should say, sorry, vapor pressure of a liquid is the partial pressure exerted by the vapor when it is in dynamic equilibrium with the liquid at a constant temperature. So that is demonstrated by this diagram here. So imagine you have a beaker with a liquid, could be any liquid, it doesn't matter, let's say water, and that is covered by a jar, a larger jar, so therefore all of this is sealed from the outside. So what will happen initially is that some of these molecules of the liquid will be converted to vapor, so vaporization will take place. So you'll have these molecules going into the vapor state, and that will continue until the amount of molecules here gets to a certain level, concentration, if you will. But before that, what you'll find is that the rate of vaporization will be greater than the rate of condensation. So some of the molecules will be going back to the liquid state, and that will be condensation. So that will continue until you reach a point of what we call dynamic equilibrium, where the rate of vaporization is equal to the rate of condensation. So when that happens, the amount of liquid here will remain constant, the amount of vapor above will be constant, but there'll be a back and forth between the two states, right? As soon as a molecule goes into the gaseous state from the liquid state, a molecule from the gaseous state will go into the liquid state, all right? So you have that back and forth taking place at this point. When you get to that point, the vapor, the pressure exerted by the vapor here will be equal to the vapor pressure. So that's what the vapor pressure of a liquid is. It is a vapor pressure exerted by the vapor of a liquid at equilibrium with the vapor surrounding it, all right, of that same liquid. Okay, and what you see here is a table of the vapor pressure of water at different temperature. Let me go back here to explain that, and I skipped it, so let me make a point of it now. If you increase the temperature of the liquid, then you're going to basically move more molecules into the vapor state, and therefore the amount of vapor here would increase, and therefore the vapor pressure would increase. So the higher the temperature, the greater would be the vapor pressure. And that's what this table is all about. And this is in reference to water. So what you see in this table, you have temperature in one column and the vapor pressure of water in the other column, right? And the same is true here, and the same is true here. So you'll see that as the temperature increases, the vapor pressure increases, and that basically continues, all right? So that's basically the relationship between the vapor pressure of a liquid and the temperature of that liquid, all right? Okay, so this is basically showing you the same setup. You have your water on a hot plate, and it is covered by this jar, and basically as you increase the temperature, the vapor pressure increases until you get equilibrium between the vapor here and the temperature and the liquid water right here, all right? Now, let's define another term, the boiling point. The boiling point of a liquid is the temperature at which its vapor pressure becomes equal to the external pressure, all right? So if the external pressure is equal to the vapor pressure, then basically the temperature at which that occurs will be the boiling point. And then the normal boiling point is basically the boiling point when the external pressure is 1 atmosphere. So if the external pressure is 1 atmosphere, and that is equal to the vapor pressure, then the temperature at which that occurs, will be the boiling point of that liquid. In this case, for water, the boiling point would be 100 degrees Celsius. So if you were to reduce the external pressure, right, that means that the vapor pressure at that point, if the vapor pressure is equal to the reduced pressure, that means that the boiling temperature would decrease, the boiling point would decrease. So that's why we call this the normal boiling point, because specifically, this is a boiling point when the external pressure is 1 atmosphere. Okay, so what you'll get if you plot the vapor pressure for liquid versus the temperature, we got what is called a vapor pressure temperature curve, right? So basically this gives you the vapor pressures at different temperatures for different substances, A, B, C, and D. Now D, I know to be water, right? To be perfectly honest, I'm not sure what the others are, but I know this to be water, right? So remember we said that the vapor pressure, the temperature at which the vapor pressure is equal to the external pressure will be the boiling point of that liquid, all right? So in the case of water, let's say you have a temperature, well, let's say that the external pressure is 200 millimeters mercury, right? So if you want to find out the boiling point of water at that temperature, you look at where 200 cuts here, the curve, and then you drop a perpendicular line down here. So by my estimation, this looks like about, I know 70 is in the middle here. So this looks like about, I would say 67 degrees, right? So the boiling point of water at 200 millimeters mercury would be about 67 degrees, all right? So in terms of the normal boiling point, remember the normal boiling point would be the temperature at which the vapor pressure is equal to 1 atmosphere, which is 760 torr. So basically, based on this diagram right here, we can see that the normal boiling point of water is 100 degrees Celsius, right? And basically, you can apply the same idea to all the other liquids whose curves are shown here. As I said before, I don't know what these liquids are, but let's say we look at liquid B, right? And you're asked for the normal boiling point of liquid B, then at 760, it looks here like the normal boiling point of liquid B is just under 80 degrees Celsius, all right? And you can do the same thing for liquid B and A, all right? Oh, sorry. What I did a while ago was for liquid C. Liquid C has a boiling point of just under 80 degrees. Liquid B would have a boiling point somewhere down here, which looks like close to 64, 65 degrees, etc. All right, or maybe even lower than that. All right, so that's how you determine those values based on these vapor pressure temperature plots. Okay, another term I want to define here called the critical temperature. And this is the highest temperature at which a liquid and vapor can coexist in equilibrium as physically distinct states of matter. Excuse me, I'm sorry. So of course, we can easily distinguish between the liquid state and the gaseous state, right? Even visually, we can see the difference between the two, all right? But there comes a point in the temperature and at a particular pressure where you cannot make a distinction between the liquid and vapor states, right? They coexist in equilibrium, but you cannot basically see the difference between them. Now, so the critical temperature is the highest temperature at which a liquid and vapor can coexist in equilibrium as physically distinct states of matter. And then you have the corresponding critical pressure, which is the vapor pressure at the critical temperature. So if you look at a plot of pressure versus temperature for any substance, you'll get this sort of diagram. We're going to talk about this in more detail, right? But at this point, I want to highlight what is called the critical point. And the critical point is this point right here, right, in this diagram, beyond which you cannot tell the difference between the liquid state and the gaseous state. And we call any state above that point, we call it the supercritical fluid. That's what we call it, SCF, all right? So that's basically what the critical point, which is C here, is all about. It's a point where, beyond which you cannot tell the difference between the solid state, the gaseous state and the liquid state. Okay, so just to give you a pictorial representation of what we're talking about with respect to the critical point, here we have a little tube which has some water in it. Obviously, you can tell the difference between the gaseous state, which is above the water here, and the liquid state, which is down here. And of course, if you increase the temperature, but you have not gone beyond the critical point, you're going to have more gas or vapor above and less of the liquid molecules below, all right? And then when you get to the critical temperature, what do you see here? You cannot make a difference between the two, right? The entire tube is filled with water, but it's now in a state that we call a supercritical fluid, where we cannot distinguish between the solid state, I keep saying the solid state, the liquid state, and the gaseous state, all right? So that's basically what the supercritical fluid is all about. Okay, so these are some different substances and their values in terms of temperature and pressure at the supercritical, just at the supercritical point, all right, in the plot that I showed you before. So these are just some examples, hydrogen, nitrogen, and so on, and their numbers, all right? Okay, so let's talk about the phase changes involving solids. Now, when it comes to solids, if you have the conversion from a solid to a liquid, we all know that is called melting. Another term that is used is fusion. So fusion, melting, same thing, all right? And the temperature at which a solid melts is its melting point. And in fact, to be perfectly honest, this is not the correct definition of the melting point. Let me just make some changes here. The temperature at which, let me just cross this out here. Let me cross this out here. The temperature at which there is an equilibrium between the solid state and liquid state is the melting point, all right? So that's the actual definition of the melting point. It's a temperature at which you have an equilibrium between the solid state and the liquid state, all right? Now, we can calculate what is called, or we can determine experimentally, what is called the enthalpy of fusion, which is the amount of heat needed to melt 1 mole of a solid. And that is the enthalpy of fusion, all right? Now, another phase change that solids will undergo is called sublimation, right? Now, sublimation is basically what happens when you have the solid state transitioning directly to the gaseous state without going through the liquid state, all right? One good example of this is iodine. If you take iodine solid and place it in a flask and you stopper it and you wait a while, at room temperature, eventually what happens is that you're going to see the entire flask colored purple. And that's because what you have in this case is a sublimation of iodine to form iodine vapor, all right? So the equation for that transition is I2 solid going to, solid going to I2 gas, all right? So that's the sublimation of iodine solid, all right? And there's a relationship between the sublimation, enthalpy of sublimation, enthalpy of fusion, and enthalpy of vaporization. So that's a relationship right here. Enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. And I can show you how that equation is derived by doing this. So here we have I2 solid going to I2 liquid, all right? The enthalpy of this is enthalpy of vaporization. And then I2 liquid going to I2 solid, I2 gas, I'm sorry. And the enthalpy change here, no, actually this is enthalpy of fusion. Sorry about that. So this is enthalpy of fusion. This is enthalpy of vaporization. So when you add these two equations, if you remember Hess's law, You cancel out the common items on both sides. So what are you left with in this case? I2 solid going to I2 gas, right? And this is called, of course, the enthalpy change for this is enthalpy of sublimation because you're going from the solid state to the gaseous state. And that will be equal to the sum of these two, which is the enthalpy of fusion plus the enthalpy of vaporization, all right? So that's how we get this equation here, which I showed you in the slide a while ago, all right? The enthalpy of sublimation will be equal to the enthalpy of fusion plus the enthalpy of vaporization. Okay, so that's as far as sublimation and fusion is concerned. Okay, so these are just some different substances and the enthalpy of fusion. And as you can see, metals tend to have a high amount of energy required to melt them compared to other substances. Okay, so that's as far as that is concerned. And what you see here on this diagram is what we call the heating and cooling curves, right? So this shows you basically the change in temperature as time progresses as you continually heat a substance. So for example, in the case of water, if you start from below the freezing point, a certain amount of energy is needed to heat it, to melt it. So as you increase the temperature, as you continue to add heat energy to the substance, water or ice, I should say, the temperature continue to rise until you get to the freezing point. And then what happens is that the solid is converted to the liquid, and that takes some time. But you'll notice that during that time, the temperature remains fixed at the melting point, which is 0 degrees Celsius. When all the solid has been converted to liquid, then you have, again, the corresponding rise in temperature. Whoops, sorry. And that continues pretty much forever, as long as you continue adding heat to the substance. And basically, this is showing you the reverse of what happens. This is called the cooling curve. Things are slightly different for reasons which I won't get into, but basically it's the same trend in the reverse order. So you have the temperature decreasing from above the boiling point to the boiling point, or the freezing point, I should say. And then that continues to flatten out as the liquid is converted to a solid. And then when all the liquid is converted to a solid, then you have the temperature decreasing again below the freezing point as heat is removed or as it cools, all right? Okay, so that's basically the heating and cooling curves. And then we're going to talk about phase diagrams, and I think this will be the last thing we're going to talk about. So a phase diagram basically is a graph which shows you the different pressures and temperatures under which you have equilibrium between different states, all right? And also even non-equilibrium states, all right? So just to explain you what we're talking about here, we have the pressure on the y-axis, the temperature on the x-axis. This line here, B to A, represents the pressures and temperatures where you have an equilibrium between the solid and the gaseous state. So we call this the sublimation curve, right? Then the fusion curve is this curve or this straight line here from A to D, where you have an equilibrium between the solid and liquid state. So that's the fusion curve. I talked about the sublimation curve already. And then the vapor pressure curve is the curve from A to C, right? So these represents the different temperatures and pressures where you have the equilibrium between between the liquid and the gaseous state, right? Now, all other points in this graph, the substance would be existing in one state or another, all right? So for example, if you choose a point, let's say right here, where the pointer is, then basically you know that at the particular temperature and pressure that it's referring to, the substance will exist as a liquid. If you have a point here, right, at the particular temperature and pressure in reference, the substance will exist as a gas. And basically any region here, right, let's say a point here, then at the particular temperature and pressure, that substance will exist as a solid, all right? The lines represent the pressures and temperatures where the different states will coexist, right? So here would be solid liquid, here would be liquid gas, and here would be gas solid. Now, this point here, okay. Well, we talked about the critical point, right? This is a point where beyond which there's no distinction between the solid, between the gaseous and the liquid state, all right? But you have this point here, which is called a triple point right here, all right? This triple point here, A, as you can see, is where you have the coexistence in equilibrium between the solid, liquid, and gaseous state. So in other words, at the triple point right here, at the triple point, you have an equilibrium between the solid in equilibrium with the liquid in equilibrium with the gaseous state, all right? So that's what happens at the triple point. Now, this diagram that you see here is true for most substances, but for other substances, you might see some slight or in some cases, some drastic variations to this general diagram. So here's one example. In the case of mercury 2 iodide, all right? You see that in the case of mercury 2 iodide, you have two different solid states, one that's called the alpha and one that's called beta, all right? So these are both solid, but the arrangement of the ions in these structures would be different. So as a result of that, you have this resulting phase diagram where you can have a transition between, let's say, the alpha and the beta type compound. And you also have two triple points. You have one triple point here where you have a coexistence of the alpha, the gas, and the solid here. And then you have another triple point here where you have the coexistence between the beta, the liquid state, and the gaseous state, all right? So this is a bit different. And the reasons why this is, which I won't get into, has to do with the complex structure of the compound that we're talking about here, all right? So this is a phase diagram for this particular compound, mercury 2 iodide. And as you can see, it's more complex than the one that we saw before. Now there's another phase diagram I want to show you, and this is for carbon dioxide. Now this one is not as complex, but again, you see some variation from the first one I showed you, where this curve here, which represents the equilibrium positions between the solid and liquid, goes up straight up and then veers to the left, all right? Again, there are reasons for that, which I won't get into, but this is just showing you again, another example of a phase diagram for a substance. And then the next diagram I want to show you is that of water. And water varies from the first one in that, in the first one I showed you, which was the general representation, this line here would be to the right, would lean to the right. In the case of water, it leans to the left. So what that tells you is that as the pressure increases, the melting point decreases. And that is true for water and not true for most substances. For most substances, when you increase the pressure, then the melting point would increase. But in the case of water, the melting point will decrease. Again, I won't go into the reasons for this, but this is, as far as I know, this is unique to water and not any other substance. All right. Okay, so that's basically the phase diagram for water. Okay, I'm going to stop here for today before I move on to dispersion forces. So before I leave here, are there any questions? Any questions?
No, sir.
Okay, all right. So let me remind you that you'll be given a test starting next week. I'll let you know in Canvas what topic. I think, let me see here. Let me remind myself. The last test, if I remember correctly, covered up to chapter, is it 5? Let me see here. Where shall I go? Where shall I go? Where shall I go? I think the last test covered up to chapter 5. Let me take a quick look. Oh, that's the lab. Okay, so let me go to the lecture. Files. Okay, where is the test folder? Okay, test. Test number. So I gave you test number 2 here. Let me see what topics was covered in test number 2. Okay, so, okay, yes, gas law, so that's chapter 5. Let me see here. I know gas laws is chapter 5, and I don't see any topics. Oh, wait a minute. Right. So basically, chapter 5 was where we stopped in test number 2. So I would say chapters 6, 7, and 8 will be the chapters covered for test number 3. All right. Chapter 6, 7, and 8. All right. So I'm going to, of course, post the answer keys to all the assignments that you have done for those chapters. So you have that to review. And if you have any questions, feel free to contact me via Skype. All right. Any questions?
No, sir.
Okay, if there are no questions, that's it for today. So enjoy the rest of your weekend, and I'll see you next